Good morning, everybody. I survived the procedure. Do I still have tattoos? No? No marks there? They drew all over my neck. I don't remember anything because the first thing they gave me was Versed. Second thing they gave me was fentanyl. I was assured by the anesthesiologist that it was the good stuff, not the street stuff. And then the third one I don't remember because by then my memory was no longer working. But yeah, no, it went well. I'm really stiff, right? Like turning my neck feels really stiff. But it takes about 4 weeks for this to kick in. So we'll see what happens. I can feel my fingers again. It's kind of amazing. So that's good. We were talking about, well, we were going to get into the mass spectrometer, but we were sort of trying to figure out what charges will do when they enter a magnetic field. And I left you with this idea that any charge moving into a magnetic field is going to not show up on the screen. Yeah, it was there and now it's gone. That any charge is going to circulate, right, in the magnetic field. So we want to take advantage of that circulation and use it maybe to figure out what different chemical things are made of. Give me a second while I fix the technology. All right. You can see stuff. I can see stuff. It happens to be recording. If I draw on the screen, does it show up? Hey! We're back in business. Okay. So I apologize today. It's going to be a little bit like drinking from the fire hose because I'm going to be throwing a lot of equations at you. Okay? And in the interest of time, I'm not going to really show you where they come from other than to say, this is what you get when you study this, right? So I'm sure you guys won't mind because you'd rather just know how to use them anyway. Actually, you'd rather be home in bed, but let's not talk about that. So the radius of this path that the charge is going to take is equal to its mass times how fast it's going, divided by the amount of charge. So it doesn't matter if it's positive or negative for this calculation of the radius. A negative charge would circulate the opposite way. So the picture we have on there is for a positive charge. It's what a positive charge follows the right-hand rule. A negative charge would arc the opposite direction. But we just use the magnitude of the charge when we're calculating this radius times the strength of the magnetic field that is in there. So knowing how much a particle will curve is going to help us in building this mass spectrometer. Okay, so a mass spectrometer consists of two parts. Well, technically, like the engineering of it is much more complicated, but in theory, an idea, this device consists of two parts. First part selects the velocity so that we have a known velocity of stuff entering the diagnostic chamber. And then the second part is where we actually measure the radius of the particles moving in there. A spectrometer is a device that's used to, the term means to kind of break apart into its elements or into its pieces. You can do spectrometry with light, in which you look at the light source and you can break it up into the individual colors of the rainbow that light source is giving off. In the case of a mass spectrometer, we're breaking up a molecule or a substance into its component parts. We want to know how many atoms of hydrogen and nitrogen and oxygen and whatever carbon might be in that sample, because as an example, you might be at a lab where you're asked to test this sample of white powder that was taken off of somebody during a routine traffic stop, right? And the assertion is that it's sugar, and we can find out, right? So how do we pull that off? So what we're going to do is we are going to, let's talk about the velocity selector first. This, again, is in no way like indicative of the actual engineering of how this works. This is just the idea, okay? So what we're going to do is we are going to take two metal plates. And on one of those plates, we are going to put positive charge on one side and negative charge on the other. Now, think back to the last unit. You put positive charge on one conductor, negative charge on the other. What's going to be between them? An electric field, right? Okay. Electric field start on positive, ends on negative. This electric field is going to be everywhere in this thing, but for clarity, I'm just going to draw the electric field right here. But it is everywhere, right, inside of this metal tube, okay? And then we are going to have a magnetic field pointed into the plane right here. Those are all supposed to be X's, but apparently I've lost the ability to draw. It never was there to begin with. So here's our magnetic field, and again, it is everywhere inside there, and I did kind of draw this one everywhere because this is what we're after. All right, and then we're going to send a particle at speed v into this velocity selector. So as the name implies, we get to pick the velocity of the particles moving through here. And it's kind of nifty how this happens. In order for anything to travel in a straight line, it can't be pushed or pulled, right? The net force on it has to be zero. So let's take a look at the magnetic field force, the Lorentz force on this particle, right? Let's get our right hands all warmed up and refreshed here, right? Okay. So we're looking for the force from the magnetic field on this particle, right? So what does our thumb do? Goes in what does it follow? Our thumb goes with what? The velocity. Okay. So we would put our thumb pointed to the right. Okay. And then what do we need to do with our fingers? What direction do they point in? They go with the magnetic field, don't they? Right? So I start with my thumb, I put it to the right, and then I turn my wrist so that my fingers can point into the screen. Okay? And then I'm left with my palm. And which way is my palm pointing? Up. Okay? So that means that this particle is going to feel a magnetic force, the Lorentz force, acting upwards on it as it travels through. Now, if that were the only force, it would curve. And we don't want that to happen. But we've got another force here. Where's the other force coming from? The electric field, right? And we know that for positive charges, the direction the force from the electric field is the same direction as the electric field itself. So there's the force from the electric field. Two forces, right? And the condition we want, okay, is that these two forces are exactly the same. Again, we need the forces to balance so that the path of this particle through the velocity selector is nice and straight. The other way the reverse way to think about this is that only particles that are moving at that speed will move in a straight line. If the particle moves too slow, which one of these forces wins? Now remember, only one of these forces depends on the velocity. Which one? Magnetic or electric? Magnetic, right? So if the speed is too slow, which is the stronger force? It's the electric force that's stronger. Because the electric force doesn't care how fast it's going, right? All it cares about is the charge. So if the speed is too slow, the magnetic field loses, and this particle would curve downward and hit the negative plate. Now, if the speed is too big, then the magnetic field force wins, and the particle would curve up and hit the top plate. Only particles that have the right speed will be able to take that straight line path through. Well, since we know that the Lorentz force acting on a charge, right, and we're at 90 degrees here between the velocity and the magnetic field, so no signs, has to be equal to the force from the electric field. Notice what cancels out. Yeah, the actual amount of charge. So it doesn't depend whether this thing is like singly ionized or doubly ionized or whatever, right? Okay, it doesn't matter. It just, right? And then this magical velocity is going to be the electric field in the selector divided by the magnetic field in the selector. Kind of a nice way. And now this can be tuned, right? As the experimenter, ideally, we would have the ability to choose this electric and magnetic field to get whatever velocity we want, right? Anything that's going faster or slower than that, it's not going to make it through. So, first part of the puzzle in place. Now, we take that velocity selector. It's right here. So, I made a big one over on the left. Now we're going to make the tiny one. And we're going to put this velocity selector, we're going to attach it to a chamber. Okay? And inside this chamber, there's going to be a different magnetic field. This is where it gets really fun and complicated and interesting. Okay? So there was a magnetic field inside of our velocity selector. I'm going to use, let's see, does your book use a different, no, your book is not careful about this. I'm going to call this one B, we say B prime. It's like a B apostrophe. In mathematics, you say prime. You can have double prime. If you've taken calculus, you might have run into this notation for derivatives. This is not a derivative. This is just another way of saying, hey, I've got a different magnetic field here, right? I can draw it in blue, which is nice, but you know, when you're working with pencil or pen or something, just being able to say, this one's different, right, than the one we had before. Okay, so now, right, if we've got a charge, right, and it's coming in with some known speed, right, now we're going to try to figure out what direction this force is going to be. And I drew this backwards, didn't I? Because if this is a positive charge, V, B, that's going to be up. I need to, sorry, you guys are going to hate me. It's the dyslexia kicking in. This is pointed out of the page. The reason I know that it has to be pointed out of the page is because I need this thing to curve, right, into my chamber. So it's going to curve around like this, okay? And then it's going to strike the wall where hopefully we have some kind of detector, right? We've got some detector along the one side of the wall there, right? And this detector will know like the distance from the velocity selector where this particle hit. Because we know the radius, right? We can solve this. We can manipulate it. And here I'm going to just jump over a few things because this is how your book defines this mass. And we'll just go with your book's definition. It turns out that the mass, again, we're kind of solving the thing there in the box by putting together what we know from the velocity selector and all that kind of stuff. This mass is equal to E. This is the charge, this is elementary charge. 1.6 times 10 to the minus 19 coulombs. It's the charge on the electron. It's the charge on the proton. Again, we're not worried about whether it's positive or negative. We're just worried more about the magnitude of the charge. Times the radius squared divided by 2. And your book is going to do this kind of strangely. It's going to throw a V in. But that V, that's voltage. What your book does is they say, well, you know, you really can't control the electric field, but what you can control is the voltage between the plates. So I don't kind of like doing it this way because too many V's flying around, right? But we'll stick with what your book does. It's just fine. It'll work out, okay? Times B squared. So like with this right here, right? And this B, by the way, is the B prime in my picture. If you know the voltage in your velocity selector and you know the magnetic field in the chamber, you measure the distance that these particles are hitting on the detector, and you can know exactly what their mass is. And the mass, like if it's a really small mass particle, it's going to have a really tight radius. Okay? And if it's a bigger mass particle, it's bigger. And if it's really heavy, right, it's going to go down there. So this measurement of distance. So what this machine is doing is it's separating out the different masses of the different molecules and elements and atoms that this sample happens to be made out of. A mass spectrometer looks like that down in the corner. It's basically a box. You stick your sample in. It does the magic. Part of this magic is taking the sample and obliterating it. It has to blow it up into its constituent parts, and all those parts need to be gathered and sent through the mass selector, and you need to run this a lot of times to make sure you get enough of the sample. But here is an example, okay, of what the output might look like from a mass spectrometer. Different units have different abilities and different software and per the manufacturer and all that kind of stuff. But in the end, a mass spectrometer can give you an idea, right, of how intense a certain ratio, it's mass to charge ratio down here. So we can see for glucose, what's glucose? It's a type of sugar, okay? So we can see here that we've got all of these different sort of peaks that are hitting for glucose. And the glucose molecule will always have this relative size and strength and distribution of peaks. This is a fingerprint, right, for the molecule that is glucose, right? And so you can send a sample through the machine of pure glucose, get its fingerprint, and then you can test another sample and compare and contrast. Here is another one for a different white powdery substance, right? Okay. So instantly, because the molecule's different, it's going to have a different fingerprint, right? Okay. And the reason we talk about this is not just because there's chemistry majors in here, or people going through the Chem-Tech program, but just wanting to show you that there are direct applications for all of this kind of weird esoteric magnetic field stuff that we've been talking about, this electric field stuff that we've been talking about. In physics, we get all excited about the fields themselves, right? Where they come from, what they do. But there are these practical applications that fall out of the application of last unit stuff with the electric field and the electric force, and also the force that happens to be on moving particles in a magnetic field. Okay. Changing gears, okay? So that was from last time, just kind of the leftovers for what happens to a charge when it moves in a magnetic field. It gave us some equations, it gave us this concept and idea of the right-hand rule, and we had to come up with a way to talk about the directions of forces in and out of the screen. So we had our X's, we had our dots, right? We developed a vocabulary. So we want to use all of that vocabulary to now extend the idea of not just a single charge in a magnetic field, but a whole bunch of charges in a magnetic field. And if you take a bunch of charges and you line them all up and you send them in one direction, that's called current. I mean, that's what a current in a wire is. So we're going to extend this idea of many charges in a row, and we're going to add up all of those QVBs that are happening to those charges into one master equation. And there it is, okay? So instead of QVB, we have ILB, but all of the same rules apply. If you just see, if the book or me or somebody just says, well, the force on a current carrying wire in a magnetic field is just ILB, well, what do you know? If the sine theta is gone, what do you know? The something's 90 degrees, right? Okay. Well, when we had QVB, it was the V and the B that were 90 degrees to each other, right? So what do you want to pick up here as to being 90 degrees to each other? You get to pick two things. The current and length. Actually, those are in the same direction. Because like length's not a vector, right? Actually, in physics, we do treat it as a vector. Okay. But for this level, for you guys, just look at the current. Whatever direction the current's flowing in the wire, that's one of your directions. And then you compare that with the magnetic field. Just like the charge is moving along, right, its velocity, we're just going to sub in current for velocity here, okay? And it's not a single charge, it's a lot of charges, so we got the length. Anyway, this comes out in newtons, like magically, right? You take an amp times a meter times a Tesla, you get, who knew, a newton. Don't try to figure it out, honestly. Just use standard SI units. It'll work out for you. Otherwise, you go down a rabbit hole, and it's terrible. All right, so what about all the right-hand rule business for this, right? Give me this is a pick your own adventure. Give me a direction for a magnetic field. Up, down, left, right, in, out. In? So let's see, we'll do, this will be our B field, and we'll make it into the page. All right, give me a wire. Up, down, left, right. Down. So there's a wire, okay, and it has current flowing downwards in it, right? So now we need to find the force on this current carrying wire in this magnetic field. The force is going to be applied everywhere along this wire. I'm only going to draw one vector, but the whole wire experiences this force. What do you think the right-hand rule might be for this one? Think about the right-hand rule we had for the moving charge. We just got to adapt it to this one. So we got our thumb, we got our fingers, and we got our palm, right? So let's start with the thumb. Where would we put the thumb? It's probably the current, right? Because in our last one, wasn't it our fingers that was the field? So let's see what happens, right? So how are we going to hold our thumb? It's got to go down, right? Okay, so we got to start with our thumb down, but we've got an infinite number of ways we can point our fingers. However, we do know that our fingers go into the screen. So which way is the palm pointing? To the right. To the right. Okay, so that means that the force on this thing is going to be to the right. I only draw one vector, but it's along the entire length of the wire, all the parts of the wire that are inside the magnetic field. And then we can do variations on a theme of this, right? Any directions. We could give you the force direction and the magnetic field direction, find the direction of the current, in which case you kind of have to inverse the right-hand rules and all that kind of stuff. But this force is not small. Work? Of course not. I was thinking about it. Well, this is the day of technical difficulties. Maybe that Versed is still working. Yep, sure is. Wow, this thing's being lazy. Give me a second. Came in this morning, my laptop was like totally dead. Yeah, it just doesn't want to play this one. You're going to have to take my word for it. It's a big force. Okay, the video was supposed to show you that it like literally jumps out quite far and quite strong. But it hates us right now, so we'll skip that, which is, I hope the next videos work because they're even more important. So let's tackle this and do an application, right, of figuring out. Now, usually we don't have just a single wire in a magnetic field, okay? We're going to have loops of wire. We're going to have connections, spirals of wire, whatever shape of wire we want in an electric field. By the way, can you think of any use for a wire being pushed by a magnetic field? Like running current through a wire and having that wire move. We're doing baby steps towards an electric motor. And where do you find electric motors? Everywhere. There's one in the projector, there's the laptop, everywhere, right? Okay, so we are removing, right, these ideas forward to try and build our modern electrified society. So what do we got here? We got a loop, right? Let's draw this a loop, okay? So it's a square. That's good enough. Okay. Now, they don't tell us, right, anything kind of about these directions and all that sort of stuff. They just say it has 2 amps. So we kind of have to pick, right? And I'm just going to pick a direction. We'll say it goes counterclockwise around the loop. Sure, why not? Okay. It also says the magnetic field exists in the plane of the loop. And that's fancy words for the magnetic field has to be pointed either left or right or up or down. I'll just draw it pointing to the right. Okay. In the end, this actually doesn't, the choices of these directions don't ultimately affect the answers that we're about to get. Okay. Obviously, it'll switch the directions around, but as you'll see, the directions are going to work themselves out. Okay. So what we want to do, okay, is find the total force on this loop. And the way I'm going to do this is I'm going to divide this loop into sections here. We'll start at the top, 1, 2, 3, 4 going around. Okay. And the only reason I'm doing that is to make it easy for us to talk about what's going on. Because we know how to find the force on a single segment of wire, of current and length in a magnetic field. What we have here are 4 wires connected together, right? So what we're going to do is we're going to find the force on segment 1, the top wire. And then we're going to find the force on segment 2, then the force on segment 3, then the force on segment 4, and then we'll add all of those forces together, right? It says find the total force on the loop. That's what we're going to do. Okay? So how do we find the force on segment 1? Well, that's going to be ILB, technically sine theta, right? But here we're going to start running into a little bit of difficulty here. What do we do about the angle? First of all, do we have the current? Yeah, they gave us the current, right? Do we have the length of segment 1? Yeah, they tell us the 15 centimeters, right? Okay. And do we have the magnetic field? Yeah, we don't have to figure any of that out. That's just going to throw it in the calculator, see what happens, right? What we have to figure out is what's the angle between the current and the magnetic field. It's 180 degrees, isn't it? Look. Yeah, so the current is flowing to the left, but the magnetic field is pointed to the right. So the angle between those two things is 180. And what's the sign of 180? 0. It's 0. Okay? So it turns out that this goes to 0, so the force in segment 1 is 0. Jack didn't like that answer, but that's too bad. he made a face. Physics sometimes has been defined as finding incredibly complicated ways to write the numbers 1 or 0. So I just proved it. All right. Can you tell me what other segment is going to be 0? Kind of by symmetry. Yeah, it's going to be 3, isn't it? Why is it going to be 3? It's parallel to 1, isn't it? The angle between them is 0. So 0 or 180, sine doesn't care. It's going to be 0, right? So the way I like to think of it is if my wire is the current is lined up with the magnetic field, there's no force. Okay? So we also know that this is going to be true for segment number 3. Okay. So can we just right away just say that we know those two are going to be equal? Is the current going to be the same? Is the length going to be the same? Is the magnetic field strength going to be the same? Yes. The only difference between them will be the direction, right? But we know that magnitude-wise, notice I haven't put any vector signs over any of this stuff, right? We know magnitude-wise it's just going to be that, isn't it? Both of them are going to be exactly the same strength, okay? But now we need to go find the directions. Okay, so we need to find the direction of the force on segment 2, and we need to find the direction of the force on segment 4. We know magnitude is the same, but now how are we going to find the directions? First of all, why is there no sine theta in my magnitude equation? It should be 90 degrees, and is it? Yeah. Segment 2 is going down and the magnetic field is to the right. That's a 90-degree angle. Segment 4, same story, right? It's going up, but the magnetic field is to the right. So that's, again, another 90-degree angle. Okay. So now, to find the direction, what are we going to have to use? Right-hand rule. Okay. So let's do segment number 2 first. Okay. Which way are we going to put our thumbs? Down. We got to follow the current, right? Okay, so we put it down. Which way do our fingers point? To the right. So we've got to rotate our wrist or our body or whatever so that our thumb points down, our fingers go to the right, and therefore the force is out of the page. So force 2 is out. We can put a little like dot for force 2, and of course it's everywhere along that wire, right? Okay, let's do the right-hand rule for segment number 4. Which way do we do our thumb? It goes up because the current is up. Which way do we point our fingers? To the right. Which way is our palm pointing? In. So put an X for that one. So if the magnitudes are exactly the same and the directions are opposite, F total, F1 plus F2 plus F3 plus F4, well, we know F1 and F3 are both 0, right? We know that F2, call it plus ILB. Why did I call it plus? It's going out. And generally, out is considered positive. Okay. And then minus, it's plus a minus ILB. And why is it minus? Because it's going into the page. Those are opposite directions, right? So what's the overall answer? 0. Told you, complicated ways of writing 0. Right? So this turns out to be true no matter what shape of loop you have. I used a square, but you can do this with a triangle. Triangle is a little bit harder because the angles are weird. Okay? You can do this with a circle. You can do this with a squiggly. You can do this with any shape, size loop you want. As long as the entire loop is inside the magnetic field, any closed loop in a constant, meaning the same strength everywhere magnetic field, you will end up with a net force of 0. It's pretty kind of incredible if you think about it, that can happen all the time. But that was just the first part of the problem. There's a much longer second part that uses the T word. Okay. Okay. So this is the thing that is not 0. So what they're doing, okay, is they're attaching this loop to an axle, okay, and it says it lies in the same plane. I'm going to put this axle. I'm running out of colors. The axle is going to be black. So I'm just going to represent it as a dotted line, okay? Like think of this as another wire. It's not carrying current. It's just a structural element, right? An axle is something that you attach other things to so it can rotate, okay? And this is where the drawing is going to get a little bit scary. What I need to do is I need to take this picture and I need to redraw it to help you see something, okay? So what I'm going to do is I'm going to take the loop that kind of looks like this piece of paper right here, and I want to redraw the picture so that we look at it edge on. So the translation I'm going to do in my picture here is we're staring at a flat piece of paper, but then we're going to rotate it so that the bottom is pointed towards us, right? And the top part is pointing away. So this doesn't work in my brain, but I hope it works in yours, right? We're going to do a transformation of the picture, okay? So what would our loop look like if I push the top of it into the page and I pull the bottom out? It should look like a straight line, right? This is what our loop would look like. Our axle is running right through there. That's neither a dot nor an X. It's just the metal bar of the axle going in and out of the screen, okay? The part we're looking at, the part that's nearest us, is segment number 3. So it's got its current flowing like that. That's not terribly important. What's more important is what are F2 and F4 doing? F2, right, we said in this top picture is pointed out. So what direction will F2 be pointed in the diagram I have down here? Out in this case would be up. So we've got this, right? And you've got a vector that's pointing like this, right? Okay. And now I turn the whole thing. Got the idea, right? Okay. It was pointing out, and then I rotate it, right? And it ends up. Okay. What about F4? If it was pointing in, and we rotate this thing, now which way does it end up? It ends up pointing down. And the reason we kind of redrew this or reimagined or rotated the diagram in space was so that you could more easily see that there is torque here now. This thing is going to spin. And which way is it going to spin? It's going to spin clockwise, isn't it? Okay. It's going to gain, I'm so sorry, angular speed. Oh boy. Yeah, omega from physics 2a, okay? Because it's going to start rotating, okay? So we get zero net force, but we do not get zero net torque. If you stick a loop in a magnetic field and you send current through it, you're going to get motion. We just invented the electric motor, right? Because this is what electric motors do, right? They end up rotating because coils are attached to an axle in a magnetic field, and they'll start to spin. Greatly oversimplifying this, we're going to get into it in a little bit more detail in the next chapter, because eventually this torque will even out and it will lock the loop into one position. So we need to do something nifty with the magnetic field directions. But for now, let's just specify what this torque is going to be. The torque tau is equal to N, capital N. This is just a counting number for the number of loops you have. So if you've got 10 loops, capital N is equal to 10. If you've got 5 loops, capital N is equal to 5. You just take whatever answer we're going to get and multiply by the number of loops you have, you get the total torque. And then it's going to be the current. And then it's going to be the area of the loop, the magnetic field strength, times sine of the angle, again, lurking in there. Okay? You will see this written in a different form. You'll see mu b sine theta. This is a favorite AIs like to push out because most textbooks write it like this, where mu is equal to NIA. So they're just kind of not writing a whole bunch of letters, right? But more importantly, this mu is a vector, okay? And this vector direction is always perpendicular to the plane of the loop. I don't think I've taught you this yet. to have to take off my sweater for this one. Okay? Have I taught you about the true nature of area? Does this sound familiar at all? Okay. Okay. I need to figure out if I've taught you or not. Is area a vector, scalar, or an elephant? Scalar? That's wrong. Up until this moment, Mr. Balogh, I was with you. Now I don't believe you anymore. Okay. You were taught that to calculate the area of, say, my binder right here, what do you do? Length times height. Length times height, done, right? Okay. And you would get a number, and there was no direction associated with it at all. There never needed to be, because area is just area. What are you talking about, Mr. Balogh? Area can't be a vector. Yes, it can. Because this area is different from this area and different from this area. Did the actual value of the area change? No. What changed? Position and rotation in space. And so in physics and in mathematics, we will find the length of the vector area by just doing the length times whatever, right? And then we define the area's direction as perpendicular to the plane or perpendicular to the surface. Okay? So this binder's area right now is pointed right at you. But if I tilt it, the magnitude of the area didn't change, but its direction did. The orientation of the area matters. And this is probably the first time we're coming up against in this class where the orientation of the loop matters. Because this torque depends on whether or not the area of your loop is lined up with your magnetic field or not. Because if your loop's area vector and the magnetic field vector are both pointing the same direction, the torque would be 0 and it wouldn't move. So how do you get a loop to rotate? You got to get the area perpendicular to the magnetic field direction. Okay? And that's the way it's going to rotate. So to invent a motor that has continuous rotation, we really are kind of stuck with the direction the area is going, right? But we start changing the direction of the magnetic field very cleverly to make it all work out. So I'm sorry, you walked in here today all innocent and confident in one thing maybe, and that was, well, I know area is not a vector. Well, it is. Its orientation matters. What's even kind of more clever about this is that apparent area, the area that something is exposed to, let's say for whatever reason you guys are throwing water balloons at me, right? Okay, and all I've got is this binder to protect myself, right? Does it matter if I hold it like this versus this? Yes, right? Okay, because holding it like this would be much more effective at blocking a water balloon, right? So the effective area of my binder changes depending on the orientation if something else is coming into contact with it, right? And so we call this cross-section. Anyway, area is a vector, and it very much matters. This mu, okay, it follows the area of the loop, and by definition, there's another right-hand rule. You don't need to worry about it too much. But you can take, I call this one a hitchhiker rule. So I have a handshake, okay, which is where your hand is flat and you got your fingers pointed and your thumb out, right? Okay. The hitchhiker is where your fingers are curled into your palm and your thumbs out, okay? So you wrap your fingers around in the direction the current's flowing in the loop, and your thumb points in the direction of area, positive area, mu, all that kind of stuff, right? So if you really want to get in the nitty-gritties, you can just pull out. We're going to use the hitchhiker rule for something else here in just a second, but just trying to help your brains accept the possibility, right, that there are vectors hidden inside here. And we got to be careful, right, about this angle. Okay. All right. I calculated numbers, but I don't care. You can throw numbers in. All right. So far, I've taught you that magnetic fields are just there because everything in the universe has a magnetic field. And if you get a permanent magnet going, you just get all the atoms all lined up and you get a magnetic field. And then we sort of slyly moved beyond that and said, well, what happens if you put a charge in a magnetic field? Who cares where the magnetic fields come from? We just have magnetic fields and we got charges moving through it. And then we did currents, and now we've got torque. And please make it stop, Mr. Balogh. My brain is full. Well, I can't make it stop because now we have to talk about sources of magnetic fields, like where they come from. And one place they come from is wires themselves. Current carrying wires do experience forces in external magnetic fields, but they create magnetic fields of their own. I have a feeling I'm not going to be able to prove it, but let's see. Let's see if I can get the computer to play something. No, it simply refuses to play anything. Shoot, it's too bad because I wanted to prove it to you. Let me try one more thing. Yeah, it has something to do with how the mirroring is working or not working. And I'm not going to be, it's not a trivial fix. So, sorry. Again, you'll just have to trust me. Okay? And I'll do my best to draw the pictures of what's going on here. Okay? So, the magnetic field of a current carrying wire. Drinking from the fire hose, not telling you where these things are coming from. Okay? Maybe it's better this way. Just get it all over with at the beginning. Mu naught times the current all over 2 pi r. This is for a straight wire. Let me explain some things, okay? I'm going to draw this 2 ways, unfortunately. That's a wire in 3 dimensions. I don't know if you can see it. Current is flowing down this wire through the middle of this wire. And it's coming from like far away, and then it's here, and then it continues on for forever. Okay, it's like 3 dimensions. Okay, the magnetic field created by this current carrying wire circulates around the current carrying wire. It's concentric circles like everywhere along the wire. Doing a terrible job of drawing this. Okay? From what I consider to be a better point of view, like if we're staring at the wire as the wire comes at us out of the screen, the magnetic fields would wrap around the wire in circles. Remember I told you magnetic fields always form closed loops? Okay, so the field around a current carrying wire. Lucky for us, you're going to be able to see this in lab, just not this Monday. Right, because of the holiday. It would have been perfect because you would have been sitting in the lab. I would have given you compasses and you would have turned on wires and stuff, and you would be able to map out this magnetic field. We'll eventually do that. It's just going to be a week from this coming Monday, right? Did you guys get the announcement about the Friday and Monday? Yeah. And then also you guys get to grade me this semester. Yeah. So the evaluations hopefully will come. Has anybody gotten the email about evaluations yet? Okay. They told me that there would be emails. Administrators lie. What can I say? Happens all the time, right? So, but I do look forward to reading your comments. What the dean says, it's interesting, but not as important as yours. Okay, so, all right. What do you want to do first? The magnitude or the direction? Direction? Let's just get that one out of the way. Okay. I just introduced it to you, sort of. Okay. This one, though, you have to remember. It's a hitchhiker. Everybody get your hitchhiker thumbs out. Not seeing Alex. Extend your thumb. No. What am I looking for? We've all got pretty. Does anybody have a thumb that really sticks over? Oh, okay, look at Jack's. Jack, look at that thumb, man. Right? Okay. That's called hitchhiker's thumb. And it's very different from the one I've got. Do you see how if I try to extend mine is straight up, but Jack's like curves over? This is called hitchhiker's thumb. Thank you, Jack. Okay. I believe that one is the dominant trait. Any biologists in the room? Okay. One of these is recessive, one of them is dominant. Okay. And I know genetics is more complicated than the, what are those diagrams that crazy monk that did beans did, right? That guy, right? Okay. I know it's more complicated than that, but anyway, that was a tangent. My thumb is very straight, right? But what you're going to do is you're going to take your thumb, okay? Jack, don't overdo it. Try to keep it straight, okay? And you're going to point your thumb in the direction the current's flowing. In this case, it's flowing out of the screen. Your fingers will naturally rotate around in the direction that the magnetic field is flowing. In this case, the magnetic field is going around counterclockwise. Okay? If it helps, you might want to take your pen or pencil and then take your thumb and point it in the direction of your pencil and wrap your fingers around your pencil. You can kind of see like what your fingers are doing around your pencil. No matter like which way we put the wire. So this is where this gets a little bit hair-raising, okay? If I've got a wire that's pointed and it's got current flowing to the right, okay? How do we hold our thumbs? Direction of current. Yeah, which way would that be? To the right. If I put my pencil sort of in my palm, right? What are my fingers doing above my pencil, which is like the wire? They're do you see how my fingers are pointing at you guys, right? Out. How do we draw fields going out of the page? With dots. So I would draw dots above this wire. But as my fingers wrap around the wire, now what are my finger points doing? They're pointing in, right? It's a circle that goes around the wire. So here I'd have to draw X's on the bottom. Okay? Again, this is the difficulty. These are three-dimensional structures, but we have to draw them on two-dimensional surfaces, right? And this is the best that humanity has come up with, okay, in terms of doing it. Of course, you can get into a computer program and do it in 3 dimensions, but that requires a lot more skill and coding knowledge and all kinds of stuff to make that happen. Don't ask AI to do it. It'll just hallucinate, okay? I'm sure we'll get there at some point, but right now it's just not working, okay? So like the 2 diagrams I kind of have over here are the same thing. It's just oriented differently, right? Okay? This direction, you think like it's circulating around, but at every point, the magnetic field points perpendicular to the circle. So if I wanted to say, what's the magnetic field right here, I would draw a vector that is tangent to the circle right there. Okay? Perpendicular to the distance from the thing. Okay, distance in that equation over there, right, is distance away from the wire. In any direction, it's symmetric all the way around the wire, okay? So that distance could be down here. It's just R like that, okay? I is current, 2 is 2, pi is pi. And then there's mu naught, which has nothing to do with the last mu I just showed you. It's a universal constant. 4 pi times 10 to the minus 7. In appropriate units to make everything work out, okay? I often round this to 1.26 times 10 to the minus 6. It gets a little bit painful to have to keep typing 4 pi e to the minus 7 in calculators. So sometimes it's just easier to do 4 times pi, which is 12.6, and then e to the minus 7, move the decimal point over 1. Okay? This one's an exact answer, and the other is the approximation that I typically use in calculations. I introduced you to epsilon naught in the last unit. Remember how I told you that K, that constant that we use in Coulomb's law and the electric field and voltage and all that kind of stuff, wasn't the whole story. It was 1 over 4 pi epsilon naught. Epsilon naught was a dead giveaway that the electric field is hiding somewhere. Even if it doesn't say electric field in the equations, if there's an epsilon naught in there, electric field's involved. Mu naught is the same idea, but for magnetic fields. Mu naught, or the permeability of free space, yes, is the constant that sets the strength of magnetic fields in our universe. It's a universal constant. It's fundamental. Okay? You'll see it pop up anytime a magnetic field is involved. Okay? So epsilon naught is the permittivity of free space. Mu naught is the permeability of free space. I know, big terms, you don't have to really worry about it. All you need to worry about is it's a constant, it's a number. I'd give it to you on an exam, right? Okay? But no, if mu naught's involved, magnetic field's hiding somewhere. Even if it doesn't have a B anywhere in it. Okay? Magnetic field is there. Okay, so that's how to find the strength of a magnetic field around a wire. What happens to the strength as you get further away from a wire? It gets weaker, right? So magnetic fields are stronger, okay, as you move away from wires. Okay. A wire is not the only shape that you can have.
Mr. Balogh,
What?
a wire is stronger as you get away from it?
Weaker.
Okay.
Did I say it backwards?
Yeah, you said it backwards.
It wasn't backwards in my head.
I'm also sleep deprived.
Yeah, between versed and sleep deprivation, I think we're in good shape. Okay. Instead of straight wires, you can have curvy ones. Okay. So you can have a wire, oops, that forms a loop, right? The equation for the magnetic field, okay, at the center of a loop is, make sure you do it the same way that your book does. Yes. Capital N, you guys know what that means now, mu naught I, I'm so sorry for this, 2 times R. And this is, I think, the way your book does it, and this is actually the way I prefer to do it too. The problem is there's too many R's floating around when it comes to magnetic fields, okay? This R is the radius of the loop, not to be confused with distance from a wire. You need to know that we are talking about the center, the magnetic field at the center of the loop. Loops create, so I had a wonderful video that showed you how to take, it graphically showed you in 3 dimensions how you take a straight wire with all of its magnetic fields circulating around it, and you turn it into a loop. And all of those spiraling magnetic fields all add together at the center of the loop to create a magnetic field that goes in one direction. The amount of magnetic field, the strength of the magnetic field at the center depends on the number of loops you have. So if you have only 1 loop, your N is 1. If you have 10, your N is 10. If it's 100,000, you got 100,000 for N, right? It just magnifies, multiplies the strength of it. Mu naught because it's magnetic field. I because there's current in the wire. 2 because there's always a 2 in physics somewhere. And capital R, radius of the loop. We're trying to be very careful to distinguish this from the R, which is the distance from a straight wire, right? Versus capital R, radius of the loop. Okay, how do you find the direction of this magnetic field? You could blindly apply the right-hand rule I just taught, okay? Let's say that the current is flowing around counterclockwise. Okay, so you could take your thumb, right, and put it in the direction of the loop, like say at the top of the loop. So at the top of the loop, the current is going to the left, isn't it? Wrap our fingers around, and our fingers are at the center of the loop, are coming which way? Kind of towards us, out at us, right? If we go to the left-hand side, well, the current would be pointing down. Which way do our fingers point? At the center? Still out. If we do it at the bottom? Still out at the middle. On the right? Do you see no matter how I hold my hand, my fingers always point out at near the center of the loop? So that can be a little bit like taxing on the mind, especially when you've got, so we're going to tax your brain a different way and give you a different right-hand rule. It's still a hitchhiker, but this time you're going to take your fingers and wrap them around in the direction of the current. Your thumb will point in the direction of the magnetic field at the center of the loop. So this one's wrapping around counterclockwise. I wrap my fingers counterclockwise, and which way does my thumb end up pointing? Out, right? So this would have a magnetic field pointed out at the center, right? If I did the current going the opposite direction, okay, I would wrap my fingers around clockwise around this loop, and my thumb would point in, wouldn't it? Okay. Okay. One more, just to complete the screen. Okay. So we've got straight wires. We've got loops. Okay. The last one we're going to have is a solenoid. A solenoid is a stack of loops. Oh golly, how am I going to draw this one? There you go. That was awful. And then these are like wires that are wrapping around. A solenoid is a stack of loops. If you take a single wire and you wrap it around a cylinder, okay, all the way around the cylinder, you end up with something called a solenoid. And I'll show you what these look like in lab next Monday, okay? Let's just get it down. We'll move on, okay? This is equal to mu naught times curly little n times I. I wish this could be better, but it can't. We just don't have enough symbols in physics. Curly n is the number of turns per unit length of your solenoid. So if a solenoid, like in a centimeter distance, has 10 turns, this would be 10 turns per centimeter. Just remember, if you're told like the number of turns per centimeter, you have to convert that into the number of turns per meter, because centimeters isn't a standard unit. And they'll try to trick you all the time on that. Okay. All right. And we're gonna do more with solenoids later. So kind of keep that one in your back pocket. Make sure that I've got all the parts. I think I do. All right. So we've been alluding to this right-hand rule, right? Okay. So how many right-hand rules do we have? How many have we used today? 5, depending on how you want to count. I think the answer is 2.5. Okay. There's this right-hand rule, which I call the handshake, right? The handshake is always involved in finding forces. Force on a charge, force on a wire in a magnetic field. And then you have what I call the hitchhiker, which is used for finding the magnetic field of wires. Different things, okay? So what I've done is I came up with this table. I'll make sure it's in the PDF, okay? But this table summarizes like the 2.5 right-hand rules that you will need to be familiar with, okay? Because this is just how we sort out everything when it comes to magnetism and magnetic fields, okay? Again, I've broken them into their two families, right? you have the handshake on the left, and you have the hitchhiker on the right. Notice, handshakes are always involved when you're finding the force on something, either a charge or a wire. Hitchhikers are always used when finding the magnetic field directions from wires. The reason I say 2.5 is because in the handshake rule, if it's a straight wire, we use our thumb for the current and our fingers are the direction of the field. But for a circular loop of wire or a solenoid, our fingers are the current and our thumb is the direction of the magnetic field. The way I remember this is let your fingers follow the shape of the current. For a straight wire, if you have a handshake, if your thumb's out like this, right? For a straight wire, how do I know it's my thumb that's the current? What shape is my thumb? It's straight, right? So I would line the current up with my thumb, or wherever way it's going, right? But for a loop of wire, the shape of the wire is a circle, isn't it? And the circle is my fingers, right? Wrapped around like this. So that's kind of how I keep it straight in my brain. You can choose to do something else, right? You can choose to put a table like this on your cheat sheet, whatever it is you want to do to keep them straight. But realize that we have like 2.5 right-hand rules. We got a handshake and we got a hitchhiker. It's just the hitchhiker can split into 2 forms depending on the shape of the wire. To be clear with the hitchhiker, right? Whichever one ends up being the field is what the field looks like. So for a wire, a straight wire, the field wraps around the wire in circles. But for a coil of wire, where your fingers are wrapping around in a circle, the magnetic field ends up being straight along the center of the loop or the center of the solenoid. We're going to be able to see this in lab next Monday. Okay? You'll be able to hold a magnet and see what the magnetic field is doing all the way around solenoids and loops and things like that. And hopefully that'll help kind of ground you in what's going on there. And yes, those are my hands. Yeah, I just held up my hand, used my camera, took a picture, told it to isolate my hand, and I copied and pasted it. Okay? So Mr. Balogh's hands for all time. This was one of the videos I was going to show you. If that current is running straight down in the middle of that picture, okay, then the field is going to be around like this in the flat plane of the plastic. They were going to put some, you're going to play with these next Monday. They're going to put iron filings on here and it would show you what it would look like, okay? Same thing like there, and there was another video. Okay, let's do an example. Oh my gosh. Are we going to survive? We may not survive to the end here. Yeah, we'll see. Okay, there's 3 points, A, B, C. We have to find the magnetic field at each of these points. This problem, we've done this problem before. And you're like, no, we've never done anything like this, Mr. Balogh. We did what is the force on a charge because there's other charges around it. We did what is the electric field at a point in space because there's 2 or 3 other charges. This is the same idea. What is the magnetic field somewhere, but now because of wires. So it's analogous. We've kind of been doing the same problem over and over and over again, just with different details in it. Okay, so let's do point A first. Okay, ignore points B and C. They don't matter. We're just looking for the magnetic field at point A. The magnetic field strength at point A will be the result of the magnetic field from the 10 amp wire plus the magnetic field from the 20 amp wire. Magnetic fields are vectors, and so they have magnitude and they have direction. Let's tackle the magnitude first, because it tends to be the simpler of the things to just calculate, because you're really just plugging and chugging here, right? The magnitude of any current carrying wire is mu naught I over 2 pi r. Again, I go back to my, what screen was it? This one, right? I look at my table of equations and I realize the wires I have in my problem here are all straight. These aren't loops. These are straight wires. And so we're going to produce a circulating magnetic field, and all we have to worry about is what the magnetic field looks like at point A. Okay, so the distance, well, we'll do the distances here in a second. That's the form of it, right? So what is B10 going to be? Like just the magnitude. It's going to be mu naught times the current in the 10 amp wire, which is 10 amps, times 2 times pi. And then what distance am I going to put in?
0.1.
It's going to be 0.1. Why am I putting in 0.1 and not 10 centimeters? Convert to meters. Just be safe and put everything in, right? So this will be 1.26 times 10 to the minus 6. This would be 10 all over 2 times pi times 0.1. I didn't write down what I got. It's okay, it's a number. What would B20 look like? It's going to be mu naught, current in the 20 amp wire, 2 pi. What's the distance from the 20 amp wire? 20 amp wire is down here, and we need this whole distance to point A. It's 30 centimeters, which converts into 0.3 meters. And then you would get another number in there. And then you would take those numbers and do we add or subtract those numbers? Well, we can't do anything yet because we don't know what directions they are pointing. If they're pointing in the same direction, we'd add them together, right? But if they're pointing in opposite directions, we would subtract them. So how are we going to figure out what directions these magnetic fields are pointing? Right hand rule? Which right hand rule? Handshake or hitchhike? It's hitchhike. How do you know it's hitchhike? Fields. We're looking for direction of a field, right? There's no forces involved here. It hasn't mentioned force. We're not looking for force. So this has to be a hitchhiker. Okay. By the way, when did it become okay to request a stranger to come pick you up in a car from your phone? Growing up, I was told never to hitchhike. Don't get into a car with a stranger.
Yeah, right.
There's an app for that now. All right.
You even paid them.
Yeah, you even paid them for it, right? Okay, so which way are we going to hold our thumb?
For which one?
10 amp. Let's do 10 amp first.
Right.
We got to hold our straight thumb to the right. And so our fingers are coming which way? At point A, they're coming out of the page. Okay? So it's whatever this number is, but pointed out of the page. And what about B20? It's whatever this number is. Which way do we hold our thumb? To the left, because the current in the 20 amp wire is going to the left. And our fingers at point A, since point A is above the 20 amp wire, which way are our fingers pointing? In, right? So this is number in, right? So what we're going to do, BA is going to be B10 minus B20. See how I took the vector signs off? It's whatever those numbers are. What I did in my calculator is I just got this number at 6.7 times 10 to the minus 6 Tesla. But the key point here is, right, we had to figure out whether or not, back up, we had to calculate the magnitudes correctly. But in addition to the magnitudes, we had to figure out what we were going to do. Were we going to add them or subtract them because of the directions of the magnetic fields? All right, what about point B? Same process. We're going to find the magnetic field from 10 and the magnetic field from the 20 amp wire. What's B10 going to be? Well, it's going to be mu naught times 10 all over 2 pi. And what's the distance? We're at point B, and we need the distance from this wire to point B. It's 0.1. So whatever number that is. And then B20, mu naught times 20 all over 2 pi times point. How far away is the 20 amp wire from point B? Also 0.1, okay, which is some number. Now what about the directions? Right, it's a hitchhiker. 10 amp, my thumb is pointed to the right. Where is point B, above or below the 10 amp wire? Below. Which way are the fingers? If you wrap all the way around, it's pointing in, right? So this one is in, number in. B20. Also in. Right? So it's going to be B10 plus B20, right? And since this red one came out positive, this must be pointing out. But these two, like you could think of it as like a negative plus another negative if you wanted to, okay? Or just add them together. But the number I got was I don't know. Is it 6.06? I think it's 6.06. I just can't read my writing. And it's pointed in. How would you do point C? Same way. Okay. On that one, I got 0.0002. Nope. I got, I didn't finish it for some reason. I don't know why. Maybe I got bored. What would we do for the directions, though, at point C? Because that's really kind of the important part. For the 10 amp wire that's up here, we're at point 3, right? Which direction is the magnetic field pointing at point C? In. And what about the 20 amp wire? Out. Okay. So get your directions correct. Okay. So the 10 amp wire points in, and the 20 amp wire points out. Calculate the magnitudes. Get your correct signs on them, and you'll get the correct answers. You have drunk from the fire hose. This is big. This is kind of like the biggest, toughest chapter of this unit right here. Okay, we're going to move into another one that's going to be probably as tough. Okay, a little bit less. And then the third chapter is actually the easiest of the unit. Okay, so front loading the difficulty here. I won't see you in grass because it's closed. Have a great weekend. Your homework for this is not due till next week, right?